In our previous lectures, we have studied the equivalent circuit model of a synchronous generator which is at no load before the fault. Now we will see what happens when there is a fault on a generator which was already at load. There are some differences in the equivalent circuit model of this kind of situation than the model which we have seen in our earlier lectures. Now let us see what are those differences. Let us say that this is a synchronous generator with the internal generated voltage, some voltage that I don't want to tell at this point. Let us say it is not known, and this is some external impedance. Let us say this is the impedance of transmission line, and there is now the load. Let us say this is called ZL, the load impedance, and the voltage across this load impedance is VL. All are these quantities in phasors. So this impedance ZL is having the voltage across it as VL. And the current flowing through the system is, let us say, IL, the load current. As of now, I have not shown these two quantities which are pertaining to the synchronous generator at load. Now, we have seen in our previous lectures that whenever there is some fault on the terminals of a synchronous generator, then the reactances offered by the generator are changed. What we have seen that the reactance first offered just on the initiation of the fault is XD double prime, or the sub-transient reactance. After few cycles of the fault, it is transient reactance. And finally, if we are just dealing with the current which is having a 90-degree phase difference with the generated voltage, then the direct axis reactance is used, is the steady state direct axis reactance. Okay, now we are going to consider a case when there is just going to be a fault on the system. That is, if I want to simulate a fault through this system, let us say at the terminals of the load, what I should do, let us say I connect a switch here, switch S, which closes at t is equal to 0, that is the time of the fault. Okay, so what will happen? This reactance, as we have seen earlier, will be different and it will be equal to XD double prime if we are just considering the situation when the fault has just occurred. So then this reactance is XD double prime. Now I am going to give a reasoning which is usually not found in any of the texts. However, if you want to study it further, I should tell you a book by author Concordia, Synchronous Machine or Synchronous Generator. I don't actually remember the exact name. It is a book, very old book by the author Concordia. Okay, you should refer this book to study the mathematical derivation of the actual model for the synchronous generator which is going through a fault and it was previously loaded. So we know that whenever a load is being given or some power is being given by the synchronous generator to the load, then there is an angle between the generated voltage and the terminal voltage, usually called delta, and the power transferred between the two terminals is controlled by this delta also. If I go through the equation, it is actually VTEF or EG over the reactance between these two sine delta. So you see that whenever there is load on the generator, then this delta will play some role. So this voltage will be dependent upon the load current also. Okay, so that's why I have put a question mark. Earlier, in the case of no loaded generator, this was simply written as EG, but here we cannot directly write it as EG because this value is going to be dependent upon the load current which is being supplied by the generator before the initiation of the fault, since there is something called the power angle which is going to control the power transferred, and this will go through change also. So because of this, there will be some complex action going inside the generator, and this voltage will be dependent upon the load current. So this is one of the reasoning which we can say to give some value to this voltage source when there is just the fault initiation. Let us say I give this voltage source a value EG double prime, just to show that I am considering the case when the fault has just occurred, that is the sub-transient phase. Okay. Now to see it more practically, we know that the air gap EMF, let us say this is the synchronous generator, this is the rotor. The air gap EMF, the EMF generated in this air gap is consisting of two parts: the no load generated voltage and the armature reaction voltage. These are the phasor quantities. So this is the resultant air gap EMF voltage, and this thing depends upon the load current, this depends upon the field current. So whenever there is a fault and already there is some current flowing through the generator, then I cannot directly write this as EG because this thing is going to be affected by the load current also. And we know that there is actually some difference between the generated voltage in the air gap just after the fault. As we know, in our one of the previous lectures, when we derived the relation between the leakage reactance and the sub-transient reactance, we found that this air gap EMF just after the fault was slightly smaller than EG because of the reduction in the mutual flux between the field winding and the armature winding, since some of the field is also generated in the damper winding and some is lost due to the eddy currents also and saturation also. So you see that this voltage source, as of now I don't know what is the value of this voltage source. I have given this a name as EG double prime. I have to find this value, but now we are sure that this is going to depend upon the load current which was flowing through the generator before the fault occurred. Okay. Now the only thing remaining is just to write various equations of this network and I can find this value. Okay. So let us say this is point P at the terminals of the load. Now if I want to see the Thevenin network seen by between these 2 points, let us say this is point P and Q, that is across the switch, what is the Thevenin network seen? It will be a voltage source V Thevenin in series with some impedance Z Thevenin, and there is this the switch. Okay. Now V Thevenin is the voltage across the point P and Q, the open circuit voltage, and Z Thevenin is simply the parallel combination of Z external plus JXD double prime and the load impedance. So we know G Thevenin directly, the parallel combination of this and these two. Let us say this V Thevenin, the voltage here before the switch S is closed is Vf. So V Thevenin is nothing but Vf. So when this switch is closed, the current flowing through this switch, if I close this switch, is nothing but the fault current, and if I am just dealing with the sub-transient part, it is equal to I double prime, and it is equal to Vf over Z Thevenin. Let us say this is equation number 1. Now I will write two more equations from the same network that we will do in the next slide. Now let's see the second equation. I can write this voltage Eg double prime when the switch S is closed is nothing but the fault current into the impedance before this fault. It is nothing but JXD double prime plus Z external. Let us say this is equation number 2. Now I am going to put the value of Z Thevenin here. What I will get, Vf over the parallel combination of this is going to be ZL into Z external plus JXD double prime into Z external plus JXD double dash plus ZL. So these are two equations which I have got from the network. Similarly, I can also know what is the value of Vf. Vf when the switch was open, as after the switch is closed, this value reduces to 0 only, but before the switch is closed, the current flowing through it is the load current IL. This is flowing through the load. So Vf is nothing but IL into ZL. Okay, so I will see that there are these three equations. Now what I will do, I will try to eliminate this I double dash. Why? Because I need to find the value of Eg double dash in terms of the load current. So this equation number 3 shows that IL is nothing but Vf over ZL. Okay, now this Vf over ZL is here. Okay, so I can see this equation number 1 just transforms into IL Z external plus JXD double prime plus ZL over Z external plus JXD double prime. Okay, now you see this equation number 1 can be used to find the value of Eg double prime in equation number 2. That we will do in the next slide. In our previous slide, we have seen that IF or I double dash can be written as this value. So what I will do, I will put this value in equation number 2. So Eg double dash, or the voltage source equivalent for the generated voltage in the synchronous generator, to find the equivalent network of this generator can be written as, what is I double dash? It is IL over JXD double prime plus Z external into JXD double prime plus Z external plus ZL, and this is the value which is coming from equation number 2, JXD double prime plus Z external. Now this is cancelled. So you see that the value of the generated voltage or the equivalent voltage source can be written in terms of the load current which was going through the circuit before the fault occurred, just by this equation, IL into JXD double prime plus Z external plus IL ZL. I have bifurcated this term in two parts. Okay, now ILZL is the pre-fault voltage. Okay, similarly this term ILJXD double dash plus Z external, IL into this thing, depends upon the load current here IL. So this EG double prime is nothing but the pre-fault voltage plus the load current into the sub-transient reactance offered by the generator and any external impedance connected between the generator and the fault point. So you see that this generated voltage is clearly depending upon the load current. Now there was a question in one of the previous GATE exam that was quite confusing the students, what value of current to be used. Now I think I have made pretty clear that in such kind of questions where there is already some current flowing through, load current is flowing through the network, then this equivalent voltage source, its value depends upon the load current. So you should always use the load current instead of using any fault current or something else. Okay, so from this whole discussion we can summarize two more points, that is how to find the fault current whenever such a scenario occurs in the system. And what are those 2 points we will see in the next slide. In the previous slide I have derived this equation for the equivalent voltage source. Now I can modify it further. If I write the voltage here as the terminal voltage of the generator, then I can write it as, you see, VF, that is the pre-fault voltage, VF0, the pre-fault 0 represents the pre-fault value. Okay, because after the fault this value can be 0 or it can be equal to IF into the fault impedance, the impedance through the fault. Okay, plus IL Z external. This is nothing but the terminal voltage. So you see that EG double dash is nothing but V terminal plus IL JXD double dash. Similarly, if we want to determine the equivalent network of the synchronous generator in the transient period of the fault, then I will just write it as EG dash is equal to VT plus IL JXD prime, that is the transient reactance will be used. Similarly, in the steady state it will be EG equal to VT plus IL JXD. So you see that this equation transformed to a normal equation which is the right equation in steady state. So our model verifies this thing also. Now, as I told in the previous slide, that this all discussion gives us two methods to find the fault current. First one is the Thevenin method, and second one is the network solving method. So what is the Thevenin method? The method uses the Thevenin theorem. What we will do, we will just make an equivalent Thevenin network, V Thevenin, which is actually equal to the pre-fault voltage, and this will be Z Thevenin. So the current calculated through this network will just be the fault current. Okay, so this current will be true or the right value only for this part, because initially no current is flowing through this branch when the switch was open. However, after the fault only IF is flowing. So this network is going to give the right value for the current only through this branch. However, this method will not give the right values for the currents if I want to determine in other parts or in other branch of the circuit. Why? Because this circuit is just thinking or showing you the values which are being seen across these 2 points. Okay, and this point is then short circuited. It is not considering any pre-fault values. So if you want to determine the current through these branches, what will happen? You will have to determine the values of currents which were flowing through these branches before the fault occurred. Okay, so like if I want to determine the current flowing through the left branch into the fault, it will be something, let us say some fault current part, IF left side is flowing after the fault, and initially some current was flowing, let us say IL through this side. So what I will have to do, I will have to write the final current through the branch as IF left side plus IL. So the Thevenin method is going to give you the right values for the fault current only. To find the currents after the fault occurred in various other branches of the network, I will have to find the pre-fault values which was flowing through these branches also. So this method should be utilized only if you want to find the fault current flowing through the faulted part. Okay. However, if you want to find the right values in other branches, I suggest you should use this method. This method is nothing but just the method which you utilize in solving any network. That is, what we will do, we will use our various methods of solving the network, like the mesh method or the nodal analysis or any KCL, KVL to solve the network, and we will find various currents from the branches. Okay, so let us say this is the current which is found after the fault occurred. Let us say it is I1 and this is I2. Then the fault current will simply be IF is equal to I1 plus I2 through the KCL. So you see that there are two methods, however they just differ only what we need to find. This is the only difference. Now in the next lecture, what we will do, we will try to solve a numerical example by following both of these methods, so that you can grasp the fundamental idea and what is the difference between these two. So I believe that I have made two things pretty clear in this lecture, that how to determine the equivalent network model of a synchronous generator which was initially at load before the fault occurred. So it should be pretty clear in your minds now that we should always determine this equivalent voltage source value through the use of the load current. Okay, and these are just simple reactances which we have studied in our previous lectures, since we already know that the reactances offered by the machine changes during the fault. Okay, and the second point is the methods of solving these kind of networks or these kind of problems. Now these methods will be pretty clear. I know it might be still confusing to some of the students. However, it will be very clear when we will consider a numerical example that we will do in our next lecture. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.